All right, so now we start with some definitions. Suppose we have a fixed graph G. Two paths in that graph are called disjoint if they have no vertices in common. So for instance here, P1 and P2 are disjoint because they have no edges in common. We'll say that the two paths are internally just disjoint if they only intersect in the endpoints of the two paths. So for instance, P1 and P3 are internally disjoint. The starting and ending point are the same, but all the other vertices are different. Finally, we'll say two paths are edge disjoint if they have no edges in common. So for instance, P2 and P4, we see that they do not have any edges in common, but they're allowed to share vertices. Finally, given a pair of vertices x and y, a subset S consisting of possibly vertices or edges is called a separating set if x and y end up in different components of G minus S. So note here the definition of separating set depends on the choice of vertices you start with. Note here that usually we will use just vertices or just edges. So now we'll state the theorem we'll prove in the next video called Menger's theorem. Suppose we have two vertices that are distinct in a graph. Then the minimum size of a vertex separating set is the maximum number of internally disjoint xy paths. So what that's claiming is that if the smallest separating set between x and y has size 2, for instance, then we must be able to find two internally disjoint paths from x to y. And so this proof takes some effort, so we'll prove it in the next video, but for now I want to state some corollaries or similar theorems. So the main corollary of Menger's theorem is this theorem. A graph is k-connected if and only if for every x and y there are k internally disjoint paths. This makes sense because in order to be k-connected, it means for any subset of size k, G minus S is connected. In particular, given any two vertices x and y, and a separator between them, t, we know that t has to be greater than k in size, which means that based on Menger's theorem, there has to be at least k vertex disjoint paths between x and y. And so that gives you the forward direction, and then Menger's theorem is used to prove the reverse direction. Namely, if you can find two vertices that have at most k minus 1 internally disjoint xy paths, then by Menger's theorem there's a vertex separator of size k minus 1, which would mean the graph is not k-connected. Now you would expect and hope for a similar theorem about edge connectivity, and so the edge connectivity version of Menger's theorem is that for every x and y, the maximum number of edge disjoint xy paths is the minimum size of a separating edge set. And then, in a similar manner, a graph is k-edge connected if and only if for every x and y there are k-edge disjoint xy paths. As an application, suppose your graph represents a highway network. Then if your graph were k-connected, this means that if at most k minus 1 parts of your highway are under construction at a time, it's still possible to get from any location to any other location, because you can find k disjoint paths, and so at least one of them is avoiding the road closures.